Today, I'm going to discuss energy. However, before I do that, I need to discuss work. Physics-wise, work is done when a force moves an object in the direction of the force. This means that only forces acting along the direction of movement do work, while the component of forces perpendicular to the movement direction do no work. So, for example, the normal force, which is the force the floor exerts so you don't fall through it, will never do work, because it will always be applied perpendicular to the movement direction. Since we only want the component of the force, or net force, parallel to our displacement direction, we write work mathematically as W, work, is equal to the magnitude of the force, F, times the magnitude of displacement, R, times the cosine of theta, where theta is the angle between the force and displacement vectors. This is actually the more basic form of the work equation. More often, it is written as W equals the integral from point R1 to point R2 of the force dotted with the infinitesimal displacement dr. This relies on the relation between cosine and the dot product, which you might remember if you watched my vector video. It also puts the equation in integral form in case the force changes with position. These two forms are essentially the same. The integral form is just more fundamental. Now that we've discussed work, we can move on to energy, which is just an object's ability to do work. There are multiple different types of energy. However, I'm going to start with kinetic energy. Linear kinetic energy is the energy of an object in motion. If you've taken a physics course, you might remember that kinetic energy, T, is equal to 1/2 m, mass, times the velocity, v, squared. That's all fine and dandy, but I'm going to show you how to derive that. We are first going to start with the differential form of Newton's second law, which states that the force, F, is equal to the mass times the acceleration. In this case, we write acceleration as the instantaneous change in velocity with respect to time, dv over dt. Note that this is what acceleration is, the change in velocity with respect to time. Nevertheless, we take our force equation and plug it into our differential work equation. This gives us the work is equal to the integral of mass times the instantaneous change in position times the instantaneous change in velocity divided by the instantaneous change in time. Since the instantaneous change in position with respect to time, dr over dt, is just velocity, we can rewrite this as W equals the integral of m times v times dv. Then, integrating with respect to v, we get that the work equals 1/2 mv squared, our equation for kinetic energy. This shows a couple of things. First off, it tells us that the equation for kinetic energy, however, we already knew the kinetic energy equation. So, the more interesting thing it shows is that work applied to an object is the change in that object's kinetic energy. Now, there is another type of kinetic energy, angular kinetic energy, which is the energy of a rotating object. The derivation of this is exactly analogous to that for linear kinetic energy, except we use moment equations rather than force equations. However, since they are analogous, I will just write the result. T equals 1/2 I times omega squared, where I is the moment of inertia, the rotational equivalent to mass, and omega is the angular velocity, the rotational equivalent to linear velocity. From the previous section, I seem to suggest that all applied work becomes kinetic energy. This is true. The only other types of energy are stored energy, which do work on an object. Kinetic energies result from the work done on an object. All stored energies depend, one way or another, on the position of the object. However, one type of stored energy, potential energy, depends only on the position of an object. Potential energy results from conservative forces, which are forces that depend entirely on the position of an object. Some examples are gravitational potential energy, which is calculated as U, the potential energy, equals mass, m, times the gravitational acceleration, g, times the change in height, h, of the object. There is also elastic or spring potential energy, determined as U equals 1/2 k, the stiffness of the spring, called the spring constant, times the displacement from the equilibrium position, x, squared. There's also electric potential energy, where U equals V, the voltage, times the charge of the object, Q. This can also be written in a form more analogous to the gravity potential, where the potential energy equals Q times the electric field, E, times the change in position relative to a point charge, D. Note the negative derivative of all of these potential energies with respect to the position gives the corresponding forces, all of which depend only on position. Mass times gravity, spring stiffness times position, and electric field times charge all only rely on the location of the object. For the first and third equations, this isn't obvious in their current forms, these forms which assume that the field acting on the objects is uniform, but in their official equations, which account for non-uniform fields, they're actually proportional to 1 over the distance between the objects, r, squared. Note that the negative in taking the derivative just indicates that potential energy increases when going in the direction opposite of the force. This is, of course, true. For example, you have more gravitational potential energy when you are higher up, which is opposite of the downward direction gravity pulls you. Pretty much it indicates potential energy is storing the force energy. Closely related to potential energy, we have magnetic energy. However, while a lot of parallels exist between electric fields and magnetic fields, magnetic forces are not conservative, so magnetic energy is not potential energy. Rather than depending on the position of an object, magnetic energy depends on the orientation of a magnetic dipole moment in a magnetic field. A magnetic dipole moment exists whenever you run current in a circle. This could simply be a wire bent into a circle with a current running through it, or something less tangible like a spinning electron. Either way, you can calculate the magnetic dipole moment, mu, as the current, I, times the area, A, of the circle it is surrounding. You get the energy by finding the component of the dipole anti-parallel to the magnetic field. Mathematically, this is described as the energy equals the negative of mu dotted with B, the magnetic field. There is also thermal energy, which is the small-scale vibrations of individual atoms or molecules. Since vibrations are a form of movement, the thermal energy equation was derived from kinetic energy. In an ideal gas, which most gases can be approximated as, the energy is evenly distributed amongst all possible movement directions. Averaging the kinetic energy over all these possible directions gives us the equation 3/2 k, the Boltzmann constant, times the temperature T, equals the energy of an individual atom or molecule. To get the total thermal energy of an object, simply multiply the thermal energy of an individual particle by the total number of particles in the object. Note that this version of the energy equation only applies to an ideal gas, one that has 3 movement directions, also known as degrees of freedom. For each degree of freedom, you get a thermal energy of 1/2 K times T. So situations with a different number of degrees of freedom will have different thermal energy equations. Also note that since energy cannot be created or destroyed, only transformed, energy that is so-called lost to friction is actually transferred to other types, one of the more common being atomic vibrations or thermal energy. For this reason, thermal energy is sometimes considered waste energy. The last thing I want to mention in relation to thermal energy is heat. Physics-wise, heat is the transfer of thermal energy, just like work is the transfer of other types of energy. Heat is responsible for the evening of temperatures of 2 objects, temperature being a manifestation of thermal energy. Another way energy can be transferred is with waves. Such transfers of energy give rise to wave energy. At its most basic form, wave energy results from the kinetic energy of periodic oscillations of matter. There are 2 types of these oscillations: transverse waves, the type of wave you might see if you oscillate a string, or longitudinal waves, which is essentially the back and forth motion you see in a spring. Water waves exhibit a combination of both transverse and longitudinal waves. Sound waves are purely longitudinal. Since wave energy is ultimately kinetic, the energy of either wave can be calculated as 1/2 of the density of the medium through which the wave travels, rho, times the volume of interest, capital V, times the velocity of the oscillating particles, lowercase v, squared. You might notice that rho times v gives us the mass, so this equation has the exact same form as the kinetic energy equation. I should mention that this is for waves traveling in 3 dimensions, such as sound waves. In 1 or 2 dimensions, simply replace the volumetric density, rho, with the mass per unit length, or per unit area, respectively, and the volume of interest with the length of interest or area of interest, also respectively. Lastly, note that in 1 dimension, the particle velocity can be defined as the angular velocity of the wave times the amplitude of the wave. While we're on the topic of waves, we might as well go over electromagnetic wave energy. This is just the energy stored in a packet of light, more commonly called a photon. We can calculate this by taking Planck's constant, h, times the frequency of the light, nu. Alternatively, we can calculate the energy as h times the speed of light, c, divided by the wavelength of the light, lambda. Note the differences from classical wave energy. Light energy has no dependence on amplitude, volume of interest, or even mass. When a photon hits an atom, the energy is absorbed as an excitation of an electron to a higher energy level. The electron will promptly fall back down, releasing a new photon, balancing the energy gained. Lastly, we will discuss the energy matter has simply by existing. This may be the chemical energy of a molecule, which is just the large-scale manifestation of electric potential energy. The arrangement of atoms and their corresponding electrons relative to one another will determine how much energy a molecule has. Almost everything in our world is made out of molecules, and all molecules have some stored energy. This is why breaking things releases sound energy in the form of a snap, and burning something creates thermal energy. Going a bit smaller than molecules, we have atoms. There is a lot of energy needed to hold together protons and neutrons in a nucleus. This is why atomic bombs, which only rip apart a few atoms, release so much energy. There is also energy needed to hold the quarks together in individual protons or neutrons. These energies, which hold protons, neutrons, and the nucleus as a whole together, are provided by gluons in the strong force. However, perhaps most interestingly in the matter-related energies is that mass itself is a form of energy. Einstein related this for masses at rest with the equation E for energy equals the mass, m, times the speed of light, c, squared. Now, there may be other specific types of energy I missed, but those energies can be related to one of the main types of energy mentioned in this video. Nevertheless, hope you enjoyed it, hope you learned something, and see ya.